Welcome to Teja Statistics. Today we are learning the moment generating function. The MGF of a random variable is denoted by mx of t. Here x is a random variable mx of t. Here mx of t is equals to expected value of e to the power of tx. So expected value of e to the power of tx formula summation e to the power of tx into e to the power of tx into p of x if x is a discrete random variable. If x is a continuous random variable, minus infinity to plus infinity e power tx into f of x into dx for continuous random variable. Mx of t exists if the series or integral is absolutely convergent. The moment generating function through MGF. So mx of t is equals to expected value of e to the power of tx. As you can see, there are so many ways to derive these values. This is one of the way, the expansion of e to the power of x formula here. 1 plus tx divided by 1 factorial, tx whole to the power of 2 by 2 factorial, and so on. If you consider, as you can see, if you apply the expectation over here, expected value of any constant will become the constant only. Expected value of e to the power of tx, here t is a constant, putting outside e of x, t square divided by 2 factorial e of x square, and t to the power of r divided by r factorial, putting outside, is a constant. Next, expected value of x to the power of r. So 1 plus, this is called mu1 dash, this is called mu2 dash, t square by 2 factorial, and mu r dash, t to the power of r divided by r factorial, and so on. So here mx of t value you can write like this: summation I runs from 1 to summation I runs from 0 to r, t to the power of r divided by r factorial into mu r dash. So for easy and simple calculations, if you apply the r value in place of r equals to 0, you will get the mu0 dash, mu1 dash, and so on, like that. So for easy and simple calculation, differentiating mu r dash is equals to d to the power of r divided by dt to the power of r of mx of t at t equals to 0. So properties of MGF. So mcx of t is equals to mx of ct. Okay, so where c is a constant, you can see the expansion over here. Consider mx of t is equals to expected value of e to the power of tx. mcx of t, that is LHS, if you consider e to the power of ct into x, you can write. So expected value of e to the power of tc into x, so this can be written as tc is a constant, mx of ct or tc. So this is the first property. Next, additive property of moment generating function. The MGF of the sum of n independent random variables is equals to the product of of their respective MGFs. Symbolically, if x1, x2, x3, and so on, xn are n independent random variables, then MGF of their sum x1 plus x2 and so on xn is given by mx plus 1 of mx2 of and so on plus xn is equals to mx of t into mx2 of t and so on mxn of t. So this can be proved by considering the LHS value of x1 plus x2 plus and so on xn as t. So the e to the power of t, if you substitute this value here, then this will become, since the formula each and every term getting the t, the next step. So e power tx1, e power tx2 plus and so on, this will be multiplied in each and every term. So hence this will become mx of t1, mx2 of t and so on. This will be in the form of this. So this is called the additive property of moment generating function. Next, effect of change of origin. The effect of change of origin and scale on MGF. Let u equals to x minus a divided by h. Consider MGF of u equals to mu of t is equals to expected value of e to the power of t mu. Expected value of e to the power of t in place of u x minus a divided by h. When bases are equal, power should be added. Okay, this formula is applies here. E to the power of tx divided by h into e to the power of minus ta divided by h. So here e to the power of minus ta divided by h is a constant. Putting outside, expectation will applicable only for the variable. So this is in the form of this. So this can be written as e to the power of minus ta divided by h. So mx of t divided by n. So here MGF is not independent of change of origin and scale also. Next, uniqueness theorem of MGF. The MGF of distribution, if it exists uniquely, determines the distribution. This means corresponding to a given probability distribution, there is only one MGF. Corresponding to the given MGF, there is only one probability distribution. Mx of t is equals to my of t. X and y are identically distributed. So there are some limitations of MGF. The MGF may exist, but movements may not exist. A random variable x can have MGF and the same or all movements get the MGF does not generate the movements. So the MGF may not exist, but the movements may exist. So these are all some important concepts about this limitations of MGF. Thank you.